4 people, a capsule the size of a large SUV, traveling at 25,000 miles per hour. They've orbited the moon. They've seen Earth as a tiny marble hanging in pure black. They've done something fewer than 24 humans in all of history have ever done. And right now, they're in the most danger of the entire trip. Not during launch, not during the lunar flyby. Right now, hurtling home. Because in about 12 minutes, they're going to hit Earth's atmosphere so fast that the air itself catches fire. And the only thing protecting them is a heat shield that engineers already knew had a serious problem the last time it was tested. This is the story of what happens when you come home from the moon, why it's brutally hard, what went wrong before, and why NASA made the uncomfortable decision to fly anyway. Here's a number: 17,500 miles per hour. That's how fast astronauts travel returning from the International Space Station. Sounds insane, but we've been doing it for decades. It's practically routine. Now forget that number. Coming back from the moon, Orion hits the atmosphere at 25,000 miles per hour, Mach 32, about 40% faster than an ISS return. But here's where physics makes things brutal. Energy doesn't just scale with speed. It scales with speed times squared. That 40% difference in speed means roughly twice the kinetic energy, all of it turning into heat almost instantly. Within minutes of touching the upper atmosphere, the heat shield surface exceeds 5,000 degrees Fahrenheit. Lava sits around 2,000 degrees. The sun's surface is around 10,000. Orion lands almost exactly in between. At those temperatures, air molecules don't just get hot electrons ripped free from their atoms. The air stops being air. It becomes plasma, a superheated, electrically charged sheath wrapping the entire capsule like a cocoon made of fire. And plasma blocks radio signals completely. For several long minutes, nobody on Earth can reach the crew. Mission control goes silent. Flight directors stare at screens and wait. The astronauts, pressed into their seats by nearly 4 times their own body weight, are completely alone. No calls, no updates, just physics doing what physics does. This is why you can't take any spacecraft built for low Earth orbit and send it to the moon. The thermal environment is in a completely different league. You need a heat shield built specifically for this, something unlike anything used in routine spaceflight. The Orion heat shield is the largest ablative heat shield ever built for a crewed spacecraft, 16.5 feet across, a single curved disc on the bottom of the capsule, the face that hits the atmosphere first. The material is called AVCoat, and the way it works is genuinely clever. Most people picture a heat shield like armor, something hard that absorbs punishment and holds on. AVCoat works on the opposite idea. It's designed to times sacrifice itself. When temperatures get extreme, AVCoat chars and erodes away in a controlled fashion, and as it does, it carries the thermal energy times with it away from the spacecraft. Heat doesn't reach the crew cabin. It gets absorbed into the material, which then leaves. This is called ablation. The same concept protected the Apollo astronauts in the 1960s. For Apollo, technicians filled over 300,000 individual honeycomb cells by hand with AVCoat one by one, taking months. For Artemis, engineers modernized the process. Just 186 large pre-machined blocks bonded directly onto the capsule's titanium skeleton. Faster, cleaner, more efficient. It was supposed to be better in every way. It wasn't. In November 2022, the uncrewed Artemis I mission splashed down in the Pacific. Capsule recovered. Inspections began. What engineers found was not what they expected. At over 100 locations across the heat shield, the AVCoat hadn't eroded smoothly. It had cracked. Large chunks had simply broken off, not ablated away cleanly, but times popped off times in jagged pieces. This is called Spolation. And it's a serious problem, because when chunks break off unpredictably, the thermal models stop being reliable. You don't know where the weak spots are anymore. NASA launched a full investigation, 2 years, over 120 individual tests. Eventually, they found the answer. The AVCoat blocks weren't porous enough. During ablation, gases form inside the material and need to escape through tiny pathways. In a properly porous material, they vent out cleanly, but the Artemis I blocks were too dense. Gases had nowhere to go. Pressure built beneath the surface until it found the weakest point and times popped. The worst damage? Right at the seams between blocks. Exactly where you'd expect trapped pressure to escape. 2 years. 120 tests. That was the answer. Too dense. By the time engineers understood the root cause, the Artemis II capsule was already fully built, heat shield already attached. Replacing it meant years of additional delay. NASA had 2 choices: wait and rebuild, or fly with the existing shield and reduce the risk a different way. They chose to fly, but they changed times how Orion comes home. On Artemis I, Orion used a technique called a skip entry. Like a stone skipping across water, the capsule dips into the upper atmosphere, uses aerodynamic lift to briefly bounce back up, then plunges back in for final descent. Elegant. Gives mission planners more flexibility in choosing a landing zone. But it was exactly what caused the heat shield problem. During the skip phase, when Orion briefly left the atmosphere, heating dropped. That sounds like a relief, but it actually let thermal energy accumulate times inside, times the avcoat, without enough sustained heat to form a proper char layer. Gases couldn't vent, pressure built, chunks broke off. For Artemis II, NASA replaced the full skip with a lofted entry, a shorter, gentler maneuver that maintains consistent heating and avoids the problematic cooldown phase entirely. The trade-offs were real. Smaller landing zone range, launch windows narrowed by roughly 50%, a big reason getting Artemis II off the ground took so long. But the consistent heating profile keeps avcoat in a thermal regime where engineers have high confidence it behaves predictably. They ran over 100 additional tests to validate it. They rebuilt their models. Artemis II will be the first time this profile has ever been flown at lunar return speeds with humans aboard. Here's what actually happens during re-entry. Hours before Orion touches the atmosphere, the crew performs trajectory correction burns, tiny thruster firings to hit the entry angle precisely. Too shallow and the capsule skips back into space. Too steep and deceleration forces could injure the crew. The corridor between those 2 outcomes is razor thin. At 400,000 feet, the European service module separates. It provided propulsion, power, and life support for the entire journey, but it can't survive re-entry. It burns up behind the capsule. From this point, the crew is on their own. The heat shield takes over. Avcoat begins to char and ablate, shedding layers, carrying heat away by design. Even during Artemis I, with all the unexpected damage, cabin temperatures stayed in the mid-70s Fahrenheit. The crew would have been comfortable. The system works. The question is whether it works times cleanly times this time. Then, blackout. The plasma sheath forms. Radio goes dead. Flight directors wait. At peak re-entry, the crew experiences 3.9 Gs, nearly 4 times their own body weight, pressing into their seats. Uncomfortable, but survivable. It passes as the capsule slows. The plasma dissipates. Signals return. Mission control exhales. But Orion is still falling at around 325 miles per hour. Way too fast to land safely. Now the parachute system takes over. At 25,000 feet, the forward bay cover jettisons. 2 drogue parachutes deploy each 23 feet across, stabilizing the capsule and slowing it to around 100 miles per hour. Then 3 massive main parachutes open, 116 feet in diameter each, 310 pounds, woven from Kevlar and nylon. Together, they slow Orion from 100 miles per hour to about 17 miles per hour. 11 parachutes total. The whole sequence takes roughly 10 minutes, and the system is designed to land safely even if one main chute fails entirely. Splashdown. Pacific Ocean, off San Diego. Navy divers from the USS John P. Murtha will be waiting. As Flight Director Jeff Radigan put it, it's 13 minutes of things that have to go right. When the crew splashes down safely, most people think the mission is over. It isn't, not for the engineers. The capsule gets shipped back to Kennedy Space Center. The heat shield gets removed. And then begins a meticulous inspection, every inch of it mapped, every crack cataloged, every char pattern compared against models and against the Artemis I damage. If the lofted entry worked as predicted, clean ablation, Minimal spallation, it validates everything. The models are trustworthy. The fix worked. Artemis II, which already has a redesigned, more permeable version of Avcode in production, moves forward on schedule. But if unexpected damage appears again, even if the crew came home perfectly fine, it raises much harder questions. Not just about the material, but about whether the models NASA is building the entire program on are actually correct. The crew can land safely. The heat shield can still tell a troubling story. That quiet inspection after the headlines fade and the parade's end is what makes this re-entry unlike any since Apollo. It's not just the end of a mission. It's the answer to a question 3 years in the making. Getting to the moon is the headline. The launch, the live streams, the moment the rocket clears the tower, that's what everyone remembers. But getting home? That's the engineering. When Orion hits the atmosphere, 4 people will be trusting their lives to a 1.6-foot disk of carefully designed material, 11 parachutes, and 2 years of hard-won lessons from a mission that didn't go quite as planned. If it all works the way it's supposed to, most people watching won't even notice how close to the edge any of it was. It'll look smooth, clean, easy. That's what good engineering looks like from the outside, but now you know what it actually took. If you enjoyed this content and found it helpful, don't forget to subscribe to the channel and stay connected. Your support means a lot and helps us keep creating more amazing videos just for you. And we'll see you in the next video.